Good morning everyone. Welcome to the homework portal, Misconceptions in Physics. And today there's a solution for the yesterday's video that I had posted on electricity. Let me share my screen, just a moment. Right. Okay. This homework 2, not homework 3. Okay. Anyway. Right. Now let us start working on this. Just give me a moment. It's not been taken so far. Right. So a wire has a variable cross-sectional area. A cross-sectional area at y is double that of x. Okay. So this area is twice that of x. As at x, the current in the wire is I, the electron drift speed is v. So here the current is I, drift speed is v. What is the current and electron speed? Drift speed at y. Now you see, so these are connected together, which means the current here and current here should be the same. So here also it should be the same. See the circuit. Okay. So which means this option and this option is incorrect. Then how do you relate current and drift velocity? We know that I is equal to NEAVD, right? Or N is nothing but the number of electrons per unit volume, which remains a constant. Area differs over here, and then the drift velocity can also change. E is the electronic charge. So we need to find out what is the value of VD here, depending upon the area. So we can now write VD is equal to I divided by NEA. Or this NEA is a constant. So what I will do is some constant K divided by A. So what do we say here? You can say VD is proportional to 1 by area. Now, if area doubles, then what can happen? VD will become 1 by 2A. Earlier it was A, now it is 1 by 2A, which means what happens? Now just let me call this VD dash. This will now be proportional to VD divided by 2. Thus the drift velocity gets halved. Which is the right answer? This is the right answer. Okay. Now let us move on to the next one. The diagram shows two equal and opposite charges that are fixed in space, at which points is the net electric field directed towards the right. So where is it directed towards the right? Which means what? It's directed like this. Now let us take from here. From here, it's due to the electric field due to this, which is in attractive like this. And due to this, it's been repulsive like this. But this repulsive force is smaller as compared to the attractive force. The reason is because this is nearby to charge Q, and as a result of it, this force is more as compared to this one. So here it is going towards the right. Let us take up this one here. If I take a point here, this point will now try to pull the charge like this. We'll have an electric field here. And due to this charge, once again, we pull like this only. So which means throughout the region, it's always in this direction. If I take a point nearby here, even then the same thing happens. So what can happen? Here, this charge will hit any other charge coming nearby to it. And at the same time, this charge, if I take it taken to this point, electric field due to this line will also be attractive like this. So once again, you have a line in this direction. Now let us take up this direction. So here it is right, here it is left. Now let us take up this one here. So the positive charge is nearby to the point. So any charges that kept here will be pushed away. But there's also a negative charge. You will try to pull it, but the force will be much smaller. So net resultant force will always be directly in this direction, in the outward direction. So here also it will be towards the right. Since force and electric field are proportional to each other, so you can directly write the electric field at this point and as well as this point. It is towards the right hand direction. So the right answer is X and Z. So it is C. Okay. Now let us move on to the next one. A cell is connected in series with a resistor, and it supplies a current of 4 amperes. Supplies a current of 4 amperes for 500 seconds. Okay. 1.5 kilojoules of energy is dissipated in the cell. 1.5 kilojoules. And 2.5 kilojoules in the resistor. All right. Okay. Now the question is, what's the EMF of the cell? Now, anyway, some energy has been dissipated. Why it is dissipated? Because of the EMF, right? EMF gives you so much energy for the energy to get dissipated. So let us find what's the total energy. Total energy is nothing but 2.5 plus 1.5, which is equal to 4 kilojoules, which is 4,000 joules. It's not to be. Now, we also know this total energy is given by the formula V times I times T, right? V into I is power multiplied by time is energy. Because energy is nothing but work done. Work done divided by time is power. So I have got this one here. Now, what do we need? We need the value of V. That's the only source. V, I'll just write like this. What is the current? 4 amperes. What's the time taken? 500. Thus, I can now write V should be equal to 4000 divided by 4 into 500, which comes out to be 4 into 5, or maybe I'll cancel this. So you get 10 by 5, which is equal to 2 volt. The answer here is 2 volt. So D. Let us move on to the next one. An electron is accelerated to a potential difference of 2.5 megavolt, sorry. So an electron is accelerated to a potential difference, delta V is equal to 2.5 megavolt. What is the change in kinetic energy of the electron? What is kinetic energy? How do you relate this? Kinetic energy, which is equal to half mv square, which is also equal to Q times V, Q times delta V, right? What is Q? Electronic charge. So we should be E multiplied by delta V is 2.5 into 10 to the power of 6. Now what do we have here? What is it need? Change in kinetic energy, delta kinetic energy. So delta kinetic, I don't want to find out the value of V at all here. So I just find out delta kinetic energy is equal to 1.6 into the power minus 19 multiplied by 2.5 into 10 to the power of 6 volt. So which should now be, what is 2.5 into 1.6? So 25 into 16. I'll do one thing. I'll just remove this. I'll write this as 16 into 25 into 10 power minus 9. Here it should be by 10. And here it will be by 10. So this will be 10 power minus 21 into 10 power 6. Maybe if you have a calculator, you can try doing it. Which would be 10 to the power of minus 21 plus 6 would be minus 15. And then 25, 6, 150, 155, 25 ones of 25 plus 50 is 400, which should be somewhere around 0.04. Can I say 0.04? Or maybe, shall I put, are we doing right? 25, 6, 150, 15, 25, okay, 400 in power minus 13 are 0.4 picofarad. 0.4 picofarad. Picojoules. The moment pico comes, we are always into farads, which is incorrect. So this is joules. So the answer is C. Then, which of the following, the last one, is the best representation of the electric field lines around a negatively charged metal sphere? Okay, a negative charged metal sphere. Inside a sphere, there is an electric field, which means, so negatively charged, which means what? So this is my sphere. The charge is been completely negatively charged here like this. So when I say there is an electric field, at the center, there are field lines shown like this. Okay, it is assumed as if it is assumed that a negative charge has been present over here. So therefore, you should have a line like this. Which of them could be the right one? As you see here very clearly, D should be the right one. Thus, we have come to an end to all the 5 problems in this particular unit. And we'll continue furthermore in a few more problems in electricity. This is only a solution for yesterday's problems. Thank you, friends, for being with me and watching this video until the end. And if you really like this, do share and comment and subscribe to my channel for more updates. Thank you. Thank you once again.